In this question, we are given the structure of an addition polymer, and we are supposed to find the structure of the monomer that gave rise to this polymer. So it's related to two topics in organic chemistry, that of alkenes as well as macromolecules. Now, firstly, how do I identify there is an addition polymer? Is when you look at the structure of the polymer, you don't see any ester linkages, you don't see any amide linkages. So the entire polymer looks like that of a alkane or a hydrocarbon. Next thing that we need to recall is, given the structure of an addition polymer, how do we get the structure of the monomer? We can do it in two steps. Step number one, we need to find the repeating unit in the polymer. So given the structure of the polymer, we must find the part that repeats itself in the formation of the polymer. So from this structure, I think it's quite simple to recognize that this is the repeating unit. So step number one is to locate the repeating unit. In fact, you can draw out the repeating unit on its own. And step number two is to erase the dangling bonds and form back the double bond between the two carbons. So there you go, we have the structure of the monomer that gave rise to this polymer. Now the next difficulty lies in identifying which monomers 1, 2, 3 and 4 given in the question has the same structure or arrangement of atoms as the one that we have just drawn. Now there are two ways to solving this. First way is to look at what each carbon in the carbon-carbon double bond is bonded to. Alright, for example, we can look at carbon number 1, alright, and this is carbon number 2. Okay, carbon number 1 is bonded to a hydrogen as well as a methyl group, and carbon number 2 is bonded to a chlorine and a hydrogen. So now we can go on to look at 1, 2, 3 and 4 and see which groups are bonded to the carbon atoms in the carbon-carbon double bond. Okay, and then we'll be able to tell whether they have the same structure as what we have just drawn. For monomer number 1, we can see that carbon number 1 is bonded to also a hydrogen and a methyl group, and then carbon number 2 is bonded to a hydrogen and a chlorine. So monomer number 1 has the same structure as what we have just drawn. Monomer number 2, we can see that carbon number 1 is bonded to 2 hydrogens. From there we can tell that monomer number 2 do not have the same structure as the monomer that we have just drawn. Okay, along the same lines, if you look at structure number 3, carbon number 1 is bonded to a methyl group as well as a chlorine. So once again, if you look at the structure of the monomer that we have drawn, we don't have a carbon that is bonded to a methyl group as well as a chlorine. So monomer number 3 would have a different structure as the monomer that we have drawn. So with that, if you apply the same principles for monomer number 4, you will find that it has the same structure, and therefore the answer would be 1 and 4 only. Now the second way of solving this is to look at the longest continuous chain. What do I mean by that? If you look at the longest continuous chain in this alkene is as follows. Okay, when we look at the longest continuous chain, you can see that the chlorine atom is actually bonded to the carbon at the end of the longest continuous chain. Okay, so if we look at the wrong structures or the monomers that are not correct, and you find the longest continuous chain, you would find that the chlorine atom is actually bonded to the middle carbon in the longest continuous chain. So that tells us that monomers 2 and 3 have a different structure from that we have drawn. Now at this point, we would have already solved the question. However, some of y'all may have this additional doubt or question that whether monomers 1 and 4, do they actually have the same structure? Now, why would anyone ask that is because if you take a look at monomer 1, the methyl group and the chlorine is on the same side. They are all below the carbon-carbon double bond. However, if you look at monomer 4, the methyl group and the chlorine is on opposite sides of the carbon-carbon double bond. So do we consider them to have the same structure? We don't learn that in the context of O levels, but at higher levels we learn that the structures are different. So why are they different? It's because we will learn that in a carbon-carbon double bond there is restricted rotation. Therefore, when you have methyl group and chlorine on the same side versus methyl group and chlorine on opposite sides, they are actually different structures because you cannot freely rotate across the carbon-carbon double bond. So in this case, we consider them to be isomers. We call them geometric isomers, which you will learn in higher levels. Now the next question is this: since the structures are different, structures of monomers 1 and 4 are different, would they give rise to the same addition polymer, which is given in the question? The answer is yes. All right, because once they form the addition polymer, the carbon-carbon double bond is broken. So now the groups on the carbon atoms can freely rotate. So the orientation of your methyl group and your chlorine no longer matters in an alkane.